Thank you very much, Christelle, for the introduction, and also thank you all the organizers for this very nice conference. It's really outstanding how you make it work, and thank you for the opportunity to speak here. So I'm going to talk a bit about a joint work with Gangu, who is a grad student. But before that, I'm going to introduce a bit what Mahler measure is about. Okay, I'm sorry, I cannot go. Oh, there, sorry. Okay, so a little bit of a historical introduction. Okay, Mahler measure originated as a way to kind of a byproduct of a construction to find large prime numbers that is kind of analogous. It's a generalization of Mersenne construction. So the idea is that you take a polynomial with integer coefficients and monic. So say the roots are Ri, and then you consider the product of Ri to the n minus 1 over all the Ri's, okay? And so this is an integer number. And if you start with the polynomial x minus 2, you get 2 to the n minus 1. So you get the Mersenne sequence. And in the same spirit as the Mersenne sequence, the point is, if you have an integer number that has this structure, searching for possible divisors is easier than a given number of the same size. There are lots of restrictions on the possible divisors, and so it makes sense to look for prime numbers in these sort of sequences. Now, so this idea was introduced by Peirce about 100 years ago, and then a few years after, Lehmer came with, did some study on these sequences and realized that in order to improve the chances of finding a prime number in this sort of sequence, one needs a sequence that grows slowly. Okay, so the idea is that if n is big, then there are more restrictions on the divisors. So you want n to be big for the number of a given size that comes from this sequence. So if you want n to be big, you want the delta n to be small somehow. And so to measure the growth of this sequence, you can consider the quotient of delta n plus 1 over delta n, absolute value, and take the limit and see what happens. And if you look at each factor, so it's going to be r to the n plus 1 minus 1 over r to the n minus 1. In absolute value, this goes to absolute value of r if absolute value of r is greater than 1, or 1 if the absolute value of r is less than 1. When the absolute value of r is 1, you could have like a cyclic thing, like if you have roots of unity, so this limit may not exist. Now, this suggests the following construction for a polynomial, like before, but I'm also allowing the polynomial not to be monic. Then consider the product of the absolute values of the roots that have absolute value bigger than 1. And I keep the main coefficient if there is a main coefficient. So this is this capital N that you see to the left. And then you can also consider the logarithmic version of this is a small n. So, so what we want from the discussion that we had so far is that capital M is bigger than 1 because we want the delta n sequence to grow, but close to 1 because we don't want it to grow too fast. Or we can formulate this in terms of the logarithmic version as being positive. So a question, I mean, we can define this for any polynomial, say with complex coefficients. Now, this originated in polynomials with integer coefficients, and we may ask, okay, so what kind of values we get with polynomials with integer coefficients? And one thing that is known is when capital M of P is 1, or equivalently, when small m of P is 0. So small m of p is 0 if and only if p is a product of cyclotomic polynomials and monomials. And this is a result by Kronecker, actually, obviously not formulated in this language, but basically says what happens if the roots of a polynomial with integer coefficients have all absolute value less or equal than 1. So it turns out they have to be roots of unity or 0, and or 0. Now, in terms of the problem that originated all of this, Lehmer formulated a question in a paper in 1933. And the question is, given epsilon positive, can you find a polynomial with integer coefficients such that this measure, is actually height. So this m of p, it lies between 0 and epsilon. And by the way, starting from now on, I'm going to always talking about small m of p. So this is what is called the logarithmic Mahler measure. The reason I'm taking the logarithmic version is that it's the most natural object that can be generalized to several variables. And this is several variables is what is interesting for me. Now, going back to Lehmer's question, so he conjectured that no, we cannot approach 0, and found this 10-degree polynomial, and say, well, this is the smallest I was able to find. Okay, so the polynomial with integer coefficients that has the smallest positive Mahler measure. So what is interesting about this problem is that, okay, so this is in a paper published in 1933, and to this day, this polynomial is still the best possible polynomial that we know, and we don't have an answer to this conjecture, and it's still a conjecture. And to tie up with the original question, so here is a large prime that Lehmer found using this polynomial. Actually, using some polynomial that has a slightly bigger Mahler measure, he was able to find bigger primes. But just wanted to give you an example of that. Okay, so now the object I'm most interested on is the multivariable version of this object. So the multivariable version consists of taking an integral of log of the absolute value of p, where each of the variables moves in the unit circle, so respect to the Haar measure. Now, if we have one variable, this reduces to the formula with small m of p that I gave you before. It's a direct application of Jensen's formula. And so this is why it's a generalization. And it makes sense to we can plug inside the log absolute value, we can plug just any rational function that is non-zero. Now, there is this result that actually is not very well written in the slide because it's very hard to write precisely. I mean, not hard, but it will take a lot of space. That if we have a polynomial or rational function in several variables, we can replace all the variables by a power of a single one. And maybe we can keep that one fixed, okay? But all the other variables, we replace it by the power of the one that we keep fixed, and take the limit when all the exponents go to infinity in an independent way. So this is what is not well written here, that the limit has to be in an independent way. Say you don't want K2 to be always twice K3 or something like that. And then when we do that, the limit of these Mahler measures actually gives the Mahler measure of the polynomial or the rational function in the n variables. By the way, I forgot to mention, but it's called Mahler measure because it was Mahler who actually extended to n variables. And he was interested in results that relate bounds, that relate heights of polynomials that are products of polynomials with heights of the factors. And well, this height works very well because it's multiplicative. So this result by Boyd and Lawton that expresses the Mahler measure of an n variable rational function in terms of limits of Mahler measure of a single variable rational functions gives evidence that the definition I gave you before is a right generalization for the one variable case that we have before. But it also doesn't tell much about Lehmer's question, because basically if we find a multivariable polynomial, I mean, we could try to find a multivariable polynomial that has a small measure, but that is harder to search than just looking at single variable polynomials. Now, just a comment, okay, so basically why would we be interested in Mahler measure? Okay, so like I said, questions about distribution of values, relations to heights, other topics that I'm not going to cover in this talk, volumes in hyperbolic space, entropy of certain arithmetic dynamical systems, and the thing that interests me the most are special values of L functions. So here are some of the simplest examples relating Mahler measure to special values of L functions. The Mahler measure of 1 plus x plus y, one can relate it to the special value of the digit L function in the character of conductors 3. The Mahler measure of 1 plus x plus y plus z can be related to zeta 3, the Riemann zeta function. Another example here is a 5-variable rational function. So x, x1, x2, y, and z are the variables, and this is related to zeta 5. And in this conception can be generalized and giving formulas with special values of the Riemann zeta function and the digit a series in the character of conductor 4. Okay, but the formulas are not as nice as this simple zeta 5 on the right. Okay, they are sum of several terms when you go for more than 5 variables. So what I want to focus now has to do with Mahler measure of elliptic curves. So say we take a family of, okay, in this case is Laurent polynomials. So x plus 1 over x plus y plus 1 over y plus k. And k is a coefficient. Okay, so the variables here are x and y. And so for each k, we have a Laurent polynomial, and we can compute the Mahler measure. And that I'm going to call m of k. Now, if we take the zero locus of this, it's actually an elliptic curve. And here I'm just giving you very concretely the transformation to turn into the Weierstrass equation. And in 1998, Boyd made a systematic study of the Mahler measures of families like this one, but not just this one, several actually, and found that very often, he looked at, say, values of k up to 40 or something like that. And then as long as the curve is not singular, he will get a rational multiple of L prime on elliptic curve, the corresponding elliptic curve in 0. Now, I wrote it in a funny way. I wrote L prime divided by sk, with sk a rational number. Okay. The reason I'm dividing is that often sk is integer. So it's often 1 over an integer, if you want, the coefficient. And this is k different from 0, 4. Those are the values where we don't actually get an elliptic curve. So to give you an idea, like a more concrete idea, so here is a table with the first 20 values of k. Actually, if you go to negative, you get the same values. So this is independent of the sign of k. So I mark in red or well also italics. If you're colorblind, there's still in italics are the cases that were proven. So conductors 15, 24, 21, 48. And the other cases are simply numerical computations. So when I write the equal sign with a question mark, it means up to, okay, back then it was up to 20 decimal places, but I don't know if people revisit this, but I mean, many decimal places, more than 20. Now, the question is, why do we get such nice numbers? And it turns out that we get these numbers because in these cases, the Mahler measure actually can be seen as a period that's coming from Beilinson conjectures. I'm not going to explain what Beilinson conjectures are, but to give an idea, they are a set of statements that can be thought of generalization of BSD and Dirichlet class number formula, and many formulas that basically have a special value of an L function in one side and a regulator on the other side times some rational factors. So what happens is that the Mahler measure can be seen as the integral of some differential form that here I call eta. So it can be written as certain, and this certain integral, and this differential form actually can be interpreted as a regulator in these Beilinson conjectures. And so if things are right, one can actually relate the Mahler measure via this integral to the special value of the L function. Now, the cases that were proven are cases where the polynomial is very, very special. So the first cases that were proven were when the curve has complex multiplication, and then we have a very good understanding of the L function. But some more modern formulas were proven where the polynomial can be parameterized with modular units. Now, before those proofs, people were trying to compare Mahler measure of different polynomials. So say you have two polynomials, P and Q, that are conjectured to be related to the same L function. Then maybe you cannot prove this identity with the L function, but you can prove that the relationship between the two Mahler measures. So one is supposed to be L prime and the other is supposed to be 2L prime. So maybe you can prove that one is twice the other. Okay? And so this can be done sometimes by understanding how the regulator works. And the regulator can be written as a function of divisors of x and y in these cases. And one can deduce from relationship between P and Q, relationship between these divisors, and then that implies relationship between the regulators, and then we can read as relationships on the Mahler measure. So for example, so here are a couple of examples with that. Okay, so the first idea, the first person who came with this idea was Rodriguez Villegas, who proved the relationship that you see on top. So 7 times the Mahler measure of this Weierstrass form is 5 times the Mahler measure of this other Weierstrass form. Some cases involving conductor 15 and 24 in the table of Boyd. Before we had the identities, there were results that we were able to prove relationship between the Mahler measures that were all related to the same conductor. And also there are some relations involving very few, actually couple, literally 2 of them, involving genus 2 curves. So for genus 2 curves, we don't have any formula that is exact exactly proven. They are all conjectures, but there are relations that were proven between different families. So the result I wanted to discuss today has to do with a genus 3 curve and an elliptic genus 1 curve. So these families have been recently studied in some work by Liu and Qin, where they examine many numerical examples in the same way that Boyd did, but now with superior genus. And from their conjectures, one can predict that there should be an identity within the Mahler measure of a genus 3 family and a genus 1 family, P and Q, and this is what we were able to prove. Now, so Q has genus 1 and here is a biased model, and P has genus 3 when K is different from 2 or minus 2. Proving this is complicated because we are supposed to look at the divisors of x and y, but x and y are rational functions on this genus 3 curve. And so what we do is we use some involution. So there is an involution. These polynomials are very, very symmetric. So in this case, there is an involution that sends x, y to 1 over x and 1 over y. And when we quotient by that, we get the elliptic curve. And so there is some trick that we have to do even though the divisors of x and y, so x and y are defined on the curve CK, we can view the regulator in terms of divisors on the elliptic curve. And after we do that, then we are able to compare these two Mahler measures. So, so that's basically behind the story of how we prove the quality, and there are many, many technical steps. And here I'm including a table that with the conjectures. Okay, so basically the relationship with the L function. That is the part that we are missing. Okay, so we are only proving that M of Q is M of P, but what we would like to have is that those two numbers are equal to L prime of EK divided by the corresponding rational factor. So that's the idea of what I wanted to share with you today. So basically coming up, okay, so as a conclusion, this regulator and this relationship with the Bayesian conjectures, okay, give some understanding of these non-trivial identities between Mahler measures. Then what we would like to do in the future, obviously, is to prove exact formulas involving genus greater than 1. And something else that I didn't discuss in the talk, but I wanted to mention. So there are also some numerical examples involving 3 variables and L prime of E in -1. Okay, so which with the functional equation, this is L of E in 3. Okay, as opposed to L of E in 2 that we had before. So this is all I wanted to say. So thanks for your attention.
All right, thank you, Matilde.